In this video, we're going to cover section 1.3, rate law expressions. Now, a kinetic study often results in a rate law expression, which is an empirical relationship between reactant concentrations and the rate of a chemical reaction. It often takes the following form, where we have the rate of a reaction equated to a product of the rate constant or rate constants and various concentrations of species. So in this particular example, A is the concentration of reactant A, B is the concentration of reactant B. The superscripts, the alpha and the beta, these are considered the orders of the reaction. So alpha is the order of the reaction with respect to A, and beta is the order of the reaction with respect to B. Sometimes these are referred to as partial orders in the sense that they are with respect to a particular species. The overall order of a reaction is the sum of the partial orders. So in this particular example, the overall reaction would be equal to the sum of alpha and beta. So if alpha and beta, for example, were both 1, then the overall order of the reaction would be 2. We would refer to this as a second order reaction. Now, the letter K represents the rate constant for this particular expression, and it is independent of concentration, but is dependent upon other external factors such as pressure and temperature. The reaction order dictates the concentration dependence of the reaction rate, the overall reaction rate. The reaction order may be an integer, could be 0, or it may be a fraction. And it's also very important to remember that reaction orders have no relation to stoichiometric coefficients, and that they must be determined by experiment. There will be some examples, elementary reactions, where we specifically know the mechanistic details of a reaction, that there may be a coincidence or correlation between stoichiometric coefficient and the reaction order. But this can't be taken for granted. There is necessarily no causation between stoichiometric coefficients and reaction order. It's an experimentally determined value, and until you devise and provide experimental evidence to support a rate expression, it's really premature to comment on the reaction order for a particular system. Now let's look at an example of a rate law expression using a reaction we saw previously, where we have 4 moles of nitrogen dioxide reacting with 1 mole of molecular oxygen to give us 2 moles of dinitrogen pentoxide. The experimentally determined rate law expression for this reaction is shown. The rate of the reaction is equal to the rate constant multiplied by the concentration of nitrogen dioxide to the square multiplied by the concentration of oxygen. The reaction is second order with respect to NO2, given by the superscript 2, and first order with respect to O2, given by the not shown superscript 1. As a result, this reaction is considered third order overall. Again, the overall order is equal to the sum of the individual orders with respect to each species in your rate law expression. Notice that the reaction orders are not necessarily equal to the stoichiometric coefficients. For example, we see we have a stoichiometric coefficient of 4 for nitrogen dioxide, whereas in our rate law expression, we only see a second order dependence. All rate law expressions must be determined experimentally with respect to each reactant. And there is absolutely no insight to be gained by considering the stoichiometry of the reaction. The rate constant, given by the letter K, lowercase, serves as a proportionality constant between the concentration of various species and the reaction rate. Now, the rate of a reaction will always have the units of concentration per time. So molar seconds minus 1 will always be the units for a rate. Therefore, the units of the rate constant, K, must change with respect to the overall order of the reaction to ensure that the reaction rate has the correct units. So if you have any questions about rate law expressions, by all means, send me an email. Thank you.